Hello, today I'm going to talk about how to build logistic regression, decision tree, and neural network in Python. I will use Anaconda Spider, and the data is the diabetes data. First, we should import the data. I usually use the pandas to import the data so we can see. And this we can check the data types. So let's go. Now you can see the data is imported. Yes, here. And we can see the data types: integer, floats, and object. Then we have two functions here, which we will use in our model building. This function is to calculate the accuracy of our model, and this is the function we use to plot the confusion matrix. So let's run these two functions. So let's go to the logistic model. First, we should import the package we need. Most of the package are from sklearn. So let's go. Oh, this. Yes. Okay. Then we should set the variables. This is to copy the data so we don't use the origin data to have the model building. And this we can get the dummy variables, and we set the tested positive is 1 and the tested negative is 0. And the X, we use all the columns in our data except the class. Let's see what is the class. Oh, sorry. So we can see the class is the test result here, and let's go. And this we use the train test split function to have the train set and test set. The ratio is 20%, and we set the random state to ensure the results are the same. Oh, I didn't want that. Let's do this. Okay, then we have to scale the continuous data, and here we use min-max scaler from preprocessing package. This will make our model building much more accurate. And then we transform the train set and test set to the value between 0 and 1. Okay. Then we can build a model. We use this linear model logistic regression to build a logistic model, and we set the random state to ensure the results are the same. First, we use the train set to build a model, and use the test set to predict, and we can get the confusion matrix and return the accuracy of the model. Then we can see our accuracy is here. If we want to see much more details of our model, we should use another package, the stats models, here. And we set the constant exist, and this will return the summary of our models. Let's see. Okay, here is the summary of our model, and we should pay attention to the p-value. And this is good, this is good, this is good, this is not good at 1% significant level, and this is bad, bad, good, good, bad. So at 1% significant level, we should use this, and this to build another model. So let's reduce the variables and set the y and x as before, and have the train set and test set. So we reduce the data and use only these columns, and then it's the scalar again, because the logistic regression, we usually standardize the value, the data, so we should have the standard scalar to transform the train set and test set. Let's do this. Okay. Then we can build a model again. Oh, sorry. Okay, we use the new data to build a model again and set the random state and predict and get the confusion matrix and print the accuracy and the summary of our new model. Let's do this. So we can see this is the summary of our new model. We can see the p-value are very good at 1% significant level, and let's see the accuracy is here, and you can see the former one accuracy is here, and the accuracy is increased. So we found this new model is significant and better than the former one. So we can use this model. And finally, we can calculate the odds ratio of the coefficient. Yes, and this we get the odd ratios of all the coefficients in our logistic model. So this is the logistic model part. Let's go to the decision tree. Okay, we import all the package we need. Set variables as we did before. Okay, and have the min-max scalar to scale the data, make the data transform to between 0 and 1. and then we should build the tree. We name the path to build the tree as estimator, and we use the train set to build the tree, and use the test set to predict. And we could build the confusion matrix and plot the confusion matrix. And this will show the accuracy. So let's do this. Oh, here we should set the random state. Again. So here is the result of our confusion matrix, and you can see it here is the predict, here is the true. This is predict 0 and true 0, and this is predict 1 and true 1. 1 is for tested positive, and 0 is for tested negative. And then we can see the details of our tree. The end nodes is to calculate how many nodes are there in our tree, and then this children left is to show whether the nodes have a children left node, and the children right is to show whether the nodes have a children right nodes. So let's see. So there are 225 nodes in our decision tree, and the positive number means the nodes have a children left nodes, and the negative means there are no children left nodes, and this same reason and it is the same for the children right. So, and we can plot the tree to see what the tree looks like. Then let's do this. We need a little bit time. Oh, you can see the tree is very complex. So it is important to prune the tree. Oh, for the tree, you can see all the details of the nodes here, like the impurity, how many samples in the nodes. So for the complex tree, we should prune the tree. We define a path, like the pruning path, to prune the tree and return the CCP alphas and the impurities. Let's do this. And then we can see the relationship between the impurity and the CCP alphas. Let's plot. Now the picture shows the relationship between the alphas and the impurities. Then we can return the model development in a list. This contained all the trees from the most complex to the simplest one. And you can see the simplest tree only have one node, and the CCP alphas of this tree is here. And then we can calculate the accuracy of all the trees. Now this we can calculate the tree which built by the train set, and this is calculated accuracy of the tree which is built by the test set. Now we can see the accuracy you can see the accuracies of the test set and train set and the CCP alpha's relationship in this picture. So we need to find the best tree. We should also print the accuracy first. The accuracy is here. This is the highest accuracy, so we need to find which CCP has made the highest accuracy. So we have this. We find two CCP alphas which make the highest accuracy. So we can try which CCP we need. So we tried which CCP make the higher train score. Let's do this. Again. Okay, you can see the first CCP alphas make the higher train score, so we use this one as our best CCP alphas, and then we build the tree with this best CCP alphas. Okay, we can see the tree is not so complex. So this is the best tree we estimate. And we can see checked the accuracy is also here. Now the decision tree part is over, and let's move on to the neural network. First we import the package we need. Let's see, okay. And then we defined a function. This function is defined for get the layers of the neural network. First the input layer, and we set the hidden layer, and this dropout is to prevent overfitting, and the output layer only have one, and then is to build a model and return the summary of the model. Then you can build Oh, sorry. Then we can build a neural network. Because we have 8 columns except for the class column, so we have 8 input layer, and we fit the neural network by train set, and this epochs is to define how many times we trained with the train set. So let's see. Oh, I did not define this function, sorry. Okay. Okay, here is the result of our neural network. This input layer and hidden layer, drop out, hidden layer. Oh, no, sorry, this is not hidden layer, it is output layer. And then we calculate the loss and accuracy, and to predict with the test set and plot the confusion matrix. Okay, we can see the confusion matrix here. This 0 and 0 for this is 0 for predict, and this is for true data, and this is for negative, and this is for positive. So we can see the accuracy here is 68.83%. That's all for our neural network part. Thank you for listening.